All right, we're going to talk next about the work kinetic energy theorem. So this is actually made from using Newton's laws, and we'll get to that in just a moment. But what it's going to tell us is that the work done by external forces will be equal to the change in kinetic energy of the system, where the kinetic energy is defined as half the mass times the speed squared. So to start, we're going to begin with Newton's second law. Sum of forces external is equal to ma. And this is going to require using a chain rule. So this is actually the reason why I kind of had that chain rule problem in the past, is we need to discuss this. So acceleration can be rewritten as dv dt. We know that. And dv dt we can rewrite in terms of position as something like dv dx times dx dt. Okay, so we're going to take that definition and we're going to run with it. A is dv dx. dx dt, however, already has a meaning. That is v, the velocity. So we have a is dv dx times v. All right, so that means the sum of forces is equal to m times v times dv dx. We'll separate this to opposite sides. We have the sum of forces times dx is equal to mv dv. Now we'll integrate both sides. We'll start at some initial position and end at a final position for the force times dx. And on the other side, we'll integrate from some initial velocity to our final velocity, mv dv. On the first side, this is the simplified definition of work where we're not worrying about the vector nature of it. So we get the work done by the external forces specifically is equal to, on the other side, we integrate this, we get 1/2 mv squared, evaluated in the limits from v0 to v, which is going to be 1/2 mv final squared minus 1/2 mv initial squared. And as you can see, that last part will just be the change in kinetic energy. So we get work external is equal to the change in kinetic energy of the system. Okay, if we really wanted to figure this out in full vector form, we'd really need to split it up at this point into sum of forces in x, sum of forces in y, sum of forces in z, acceleration in x, acceleration in y, acceleration in z. That looks like it gives kinetic energy change in x, y, and z, but really we're kind of oversimplifying things here. And if you added all of the external works together in x, y, and z to get the total external work, then you'd be adding the other components together, and it will turn back into the same expression for kinetic energy because v squared is just equal to vx squared plus vy squared plus vz squared. So even if we split it into components, we can regenerate what we're used to, and we can regenerate if we choose the definition of work that we've already talked about, where we're worried about the directions of the displacement versus the forces. All right. So quick proof of work kinetic energy, and that actually was shorter than I expected it to be. I'm kind of wondering if I should show you how you can generate the whole thing in terms of components. Yeah, we've got the time. So this is a point where if you don't want to see it and you accept what I've already told you, that we can use our definition of work external from before, which, to remind you, is integral of the forces dot product the displacement vector. That's the full version of work external. If you already accept that, you can stop the video at this point and move on. Otherwise, I'm going to take this idea of components in different directions and show you how we can put them back together. So for that, we're going to think about, we have one equation that is integral x0 to x, sum of forces in x dx equal to, and it's going to come out as 1/2 mvx final squared minus 1/2 mvx initial squared. We're going to get 3 more identical equations if we consider each of the other components. So integral y0 to y, sum of the forces along the y direction dy, 1/2 m vy squared minus 1/2 m vy0 squared. And the same thing for z for completeness. So integral over fz dz equal to 1/2 m vz squared minus 1/2 m vz0 squared. Now what we're going to do is add all of these components up and see what we get. So we've got an integral between x0 and x, sum of forces in x dx, plus integral y0 to y, sum of forces of y dy, integral from z0 plus integral from z0 to z, sum of forces in z dz equals to, the 1/2 m is completely common. I'm going to pull that out in front for convenience. We get vx squared plus vy squared plus vz squared minus vx0 squared minus vy0 squared minus vz0 squared. I didn't need the parenthesis. Sorry, let me repeat what I said. 1/2 m bracket vx squared plus vy squared plus vz squared minus vx0 squared minus vy0 squared minus vz0 squared end bracket. We're going to handle the second part first. So if we think about this, vx squared plus vy squared plus vz squared is just v squared, it's just the speed. And vx0 squared, vy0 squared, not squared, plus vz0 squared is equal to v0 squared. So on that end side, we're just going to get 1/2 m v squared, the final speed squared, minus v0 squared, the initial speed squared. Let's think about this first part here. If we had an integral for the work, it's the sum of forces as a vector dot product with dr, the displacement. But the sum of forces vector we can write as the sum of forces in x in the I hat, plus the sum of forces in y j hat, plus the sum of forces in z k hat. And we can write dr in terms of dx in the I hat, dy in the j hat, and dz in the k hat. Now the way a dot product works is you can only take things that have the same hat and multiply them together. So if we actually took this integral of the force vector dot product with the position vector, that is going to become the integral of sum of forces in x dx plus sum of forces in y dy plus sum of forces in z dz. And you can see how that's going to split out. If we're thinking about our r initial and our r final as our starting and ending vectors, well, the sum of forces in x only cares about how the x component is changed, and the sum of forces in y only cares about the y, and same thing with the z. So this just will become what we already have above, that it's the integral from x0 to x, sum of forces in x dx, plus integral y0 to y, sum of forces in y dy, plus the integral z0 to z, sum of forces in z dv. So that means we can replace, going back to our equation up at the top, I'll underline it in something bright like pink. Going back to this, all the work we've just done in the middle shows that we can now rewrite that, and I'll write the final answer in yellow here. Integral of the net force vector dot product with its position vector dr is equal to 1/2 m speed squared minus speed initial squared, all in parentheses. And that can be rewritten as just the sum of forces dot product the displacement, or dr, equals the change in kinetic energy. Or, last step, we get the work external equal to the change in kinetic energy with the full vector form. Now, that was 5 extra minutes you didn't have to watch, but if you did, you probably have a better idea where all of this is actually coming from, which is cool. All right, I'm going to stop there. I'll see you in the next video.